Hey, what's up guys? This is Akshay from AS Learning, and today in this video we'll be seeing about t-sne. So t-sne is one of the most powerful dimensionality reduction techniques we have in machine learning. We have PCA, salmon mappings, truncated SVD, t-sne, and t-sne is one of the latest one, and it is one of the most powerful ones. Compared to others, t-sne is better into dimensionality reduction as per many people and experiences. Okay, so it stands for T distributed stochastic neighbor embedding. Okay, what it does is it tries to convert the higher dimensional data into lower dimensional data. uh, Technically it take into consideration the similarity between the data points. It creates joint probabilities and it tries to minimize the callback liberal divergence between the joint probabilities of the low dimensional embedding and the high dimensional data. Okay, so many jargon terms: joint probabilities, callback levels, and divergence. So in short and in simple terms, it tries to reduce the higher dimensional data into lower dimensional data. Okay, and it tries to retain the variance. Okay, so that the lower dimensional data should be a representation of the higher dimensional data. Okay, t-sne has a cost function that is not convex, hence with different initialization we can get different results. Okay, it is highly recommended to use another dimensionality reduction methods also, like PCA when it comes for dense data, and truncated SVD for sparse data. And generally what happens is when we have large number of features, okay, let's say the feature count is 300, 400, so at that time it is recommended to go with the classical old dimensionality reduction technique of PCA. It would work better instead of t-sne at those point. So whenever the features are high, PCA would work better for you. If you have dense data, then also you can try PCA and t-sne. If the features are less, definitely t-sne would do better. Okay, and let's say for dense data, PCA is better over truncated SVD. Okay, so as per the number of features and the type of data, these techniques of dimensionality or reduction have edges over each other. Okay, so yeah, so this was in short about what t-sne is. Now what we'll try to do is we'll be using the popular MNIST dataset, that is the numbers dataset, and we'll try to convert this image dataset into two-dimensional mapping. Okay, so this image dataset, we know that we have lots of pixels and each pixel has a value. Okay, so the image size and the pixel size is roughly in the range of 700 resolution. Okay, and what here we'll be trying to do is we'll be converting this high dimensional image data into two dimensional t-sne output. Okay, and we'll be seeing how the clusters are created, and we'll be seeing how it is correlated with each other. Okay, so here we have done some basic library importing. We have fetch our data set. Here we are using the version 1. Okay, so the default parameter of version is active. By active, it takes the uh, most oldest used version of the database. Okay, here I have passed it as 1, so it is taking the first version of MNIST 784 784 dataset we have. Okay, it is returning me the pixel values and the target. So I'll show you how the dataset is returned to me. Here we have the pixel values. So yeah, here you can see that we have 784 columns. Okay, and we get around 70,000 rows. Okay, and each of these columns is a representation of one of the pixel in this image. Okay, now we'll be seeing our target Okay, so here each row is nothing but our one single image. Okay, so now this image will have one single entry into this data set. Okay, so in this way we have 70,000 images with us with 784 unique pixel values. Okay, so we can say this data to be having 784 features. Okay, now we'll be mapping the 784 features to two features, two dimensions, and we'll be seeing whether do we retain the property of the MNIST original data set. Okay, here I have just plotted one single row of the data set, and here we can see that it is 0. Okay, and after that I have loaded t-sne with the help of manifold class, given it number of components as 2 because we want to map it into 2 dimensions. Okay, kept a random state of 42. Okay, and after that I have done a fit transform. The fit, this output of transform data I'll show you. Okay, I'll show you the this data frame which gets created. Okay, that would be more better. Okay, just give me a second. Yeah, so here we can see that now our data set which was in this format is being converted into a low dimensional data of only two features. Okay, now this is the dimensionality reduction aspect I was talking about, and here we can see that we have the targets, and that is the target which we had here also, and this 784 features got converted into only two features of x and y. After that we did a plotting, and this is how our MNIST dataset looks, and we can see that the original property of the dataset is retained. We can see all the ones being clustered into one side. Then in green we have 2s, pink we have 6, then we have blues as 0. Okay, only the sky blue part is distorted, and it is between 9 and I think so 4. Okay, so this is somewhat where the mapping is not properly done. Okay, but apart from this I feel everything is okay. Even some part of 5 is getting mixed with 3. Okay, but yeah, apart from that we can see that the original property of the data set is being retained by t-sne. And yeah, so I can recommend you that on for further analysis try to do a similar plotting using PCA, Salmon's mapping, truncated SVD, and then we can see the comparison, like which mapping did better on MNIST. As per me, we have 784 features, so I feel that here maybe t-sne, but here it's a sparse data. We can see it's a sparse data, so maybe truncated SVD might work better. Okay, truncated SVD might work better than PC and t-sne, but yeah, do check it out, and do let me know in the comment section if you feel that truncated SVD did better here. Okay, so that's it with this, guys. This was a small short video about t-sne. If you like this video, give it a thumbs up. Do check other videos and stay tuned to AS for more such amazing tech stuff. Take care. Peace out.